Okay, so we're now going to move on to the vector calculus part of this course. We'll be looking at the divergence and curl of electrostatic fields. We'll start this by looking at field lines, flux, and Gauss's law, which is something that you've seen before in Physics 1b, but we'll be seeing how we can move from the way that we wrote it in Physics 1b onto the vector calculus way of writing it. Okay, so as you are very aware, for a point charge, the electric field is given by this expression here, 1 divided by 4 pi epsilon naught q over r squared, and it's in the radial direction. We've already seen that in this lecture, and it's kind of like the simplest case, which is why we're starting with this one. And just to remind you, we can represent this with a figure as well. We can draw this as we've shown here. In this case, the field lines are shown going out because remember, the field lines represent the direction of force on a positive particle which is put in this electric field. So they're always away from positive charges and towards negative charges. So we've got our charge Q in the middle here. This is this Q here, which is generating this electric field. And this is, just so that we're all clear, just a 2D representation of what's going on in three-dimensional space. These field lines are really coming out of a sphere rather than out of a circle. So this is just a diagrammatic way of showing that. Okay, so that's electric field. Now, electric flux is related to, we can think of it as the number of field lines that cut through the surface. So number of field lines cutting through a surface. So it's proportional to the density of the electric field lines. If we draw the electric field lines really close together, that's showing that there's a really strong electric field, and so there's a stronger flux. And we can use this equation here to calculate it. So phi E is the symbol that we use for a flux. In this case, this integral here has a little s to indicate that it is a surface integral. So the other way we could write this is as a double integral because we are integrating over 2 dimensions. E here is our electric field, which for a point charge we've described with the equation above. And then dA, this is an increment of surface area. So the direction is perpendicular to the surface. So if we were considering this surface here, we'd take a little increment here. It's got an area perpendicular to, it's got a direction perpendicular to the surface, and the area here would be equal to dx dy. Now, obviously, if we're going to be thinking about spherical coordinates, we're going to have to use our transformation here. And so it's going to depend if we've got if we're integrating over d theta d phi or dr d phi. It'll depend on the exact surface, and we'll need to take that into account when we're working out what this dA here is. But this is just saying that if we integrate the dot product between the electric field and the surface, we end up with the electric flux through that surface, which is effectively the number of field lines cutting through a surface. Now, Gauss's law was telling us about closed surfaces. So I want you to imagine this sphere here. So I've drawn these extra lines on it to try and indicate that this is a 3-dimensional shape. Now, if we imagine putting some charge outside this sphere here, the electric field lines come away from this positive charge and they enter the surface here, but then they leave the surface over here. So charges outside our surface don't contribute to the flux through the surface because we've got as many lines going in as we have coming out, and so that cancels each other out. So what Gauss's law tells us is that the electric flux through a closed surface, so this integral here with the circle around it shows that this is a closed surface here, is equal to the charge enclosed within the surface divided by epsilon naught. So what we're going to do now is we'll show that this works for a sphere around a point charge. Righto, what we're going to do now is we're going to try and show that this equation here holds for a point charge with a spherical surface. So let's just draw our situation just so that we can be very clear. So we've got a point charge here with a magnitude Q. It's got electric field lines coming out of it like this, say. And we are going to take a spherical surface here with a radius r, and this is all in 3 dimensions. And this is a relatively simple situation, so we should be able to directly calculate all the integrals and show that the equation for Gauss's law is true in this case. Okay, so we want to find out what E dot dA is. Now, this is shorthand for writing quite a few different things. We're going to be doing a surface integral over the sphere. The sphere we're considering is all at the same radius, so it's at a constant r. So we're going to have to integrate over the other 2 variables if we're using spherical coordinates, so over d theta and d phi. We're letting d theta and d phi vary their full amounts. So we can write this as a double integral. And the electric field here, we've said for a point charge is in the radial direction. So we're writing 1 over 4 pi epsilon naught Q over r squared, and that's in the radial direction r. And then we need to take the dot product of that between a little increment of surface area. And so the surface area is going to be in the direction d theta, d phi. Well, those are the increments. It's in the radial direction as well, because we've said that the surfaces, the direction of the surface increment is always out of a closed surface. So we've drawn a little sketch of that there. And the Jacobian that we need to use in this case is r squared sine theta. So you were asked to think about that one in the pre-work. So hopefully you know where that factor of r squared sine theta comes from. Okay, so sorry, and I should have put this, I've put that bracket in the wrong place. So let's just move that bracket to the right place. So this is phi r, close the bracket. And so we're taking the dot product between 2 parallel vectors here. And because we're going over d theta and d phi, well, d theta, that's the angle with the x-axis. So that goes from 0 to pi. And d phi, that's around the circle of the xy plane. So that goes from 0 to 2 pi. So now we've got an integral that we are going to need to solve. So let's do every step. We've got from 0 to 2 pi and from 0 to pi. And then we've got 1 over 4 pi epsilon naught q on r squared times r squared. So those will cancel out. We've got sine theta, d phi. And we can pull our constants out the front. So we've got q over 4 pi epsilon naught, and then from 0 to 2 pi and from 0 to pi. Now the first integral we're going to be doing is this sine theta d theta, and then we'll do the d phi. So we've got q over 4 pi epsilon naught, 0 to 2 pi. We're doing the integral of sine theta, and when we integrate that, we get minus cos theta. And the limits on that integral were from 0 to pi, and then we've got d phi. We've got q over 4 pi epsilon naught from 0 to 2 pi. When we evaluate this, minus cos of pi, that's minus 1, so that's plus 1, and then minus cos 0, so that's plus 1 d phi. And so now we need to integrate 2, and so this is going to be equal to q over 4 pi epsilon naught, and this will be 2 phi, and we're going from 0 to 2 pi. And so this will equal q over 4 pi epsilon naught times 4 pi minus 0. And so those cancel, and we end up with q over epsilon naught. And that is the same as what this is up here, because we placed our charge q in the middle there. So this is the charge which is enclosed within our sphere here. So we've shown that this works for the case of a single point charge. And so it follows, because of the law of superposition, and because this electric flux doesn't drop off with the distance, so there's no R dependence here, because the R's cancelled out nicely in this step here. So that tells us that it really doesn't matter where in our sphere here, it really doesn't matter where the charge is, because the flux doesn't depend upon that distance. And so because this is true for a single point charge and it doesn't matter where the point charge is, it must be true for lots of point charges as well. And so we've kind of effectively shown Gauss's law there. So we were trying to get to a way to write what we know about electric fields and everything using vector calculus notation. So we're going to get to that now. We're going to be writing Gauss's law in its differential form. In order to do that, we're going to need to make use of the divergence theorem, which you have learnt about in mathematics. Hopefully you remember it. I did include it in the preparatory material for this week's lecture. So if you've forgotten a bit about it, then I recommend that you work through that preparatory material so that you're on top of it. So the divergence theorem is a way to relate a volume integral of the divergence of a field to the surface integral of the dot product between the field and the normal. So this here is our divergence. It's nabla dot, which means the divergence. F here is a vector field. And on the right-hand equation, we've got the same vector field, and n here is a normal to the surface. So down here where we've got dA is a shorthand way of writing the normal to the surface times ds. Those two things mean the same thing. It's just we've written Gauss's law here in a very shorthand notation. So just a reminder, this is what Gauss's law tells us. So now we're going to use Gauss's law with the divergence theorem to come up with a simpler way of writing down Gauss's law using vector calculus. So let's start by writing down Gauss's law, E dot dA. And like I said, this is a very, very shorthand way of writing this. So let's write out in full exactly what we mean here. So with this integral, we mean that this is a surface integral. So it's an integral in 2 dimensions. So we've got a double integral there. And then we've got our electric field here. That's our vector field that we're considering here. And we said that A was equal to, what dA is the normal times ds. So this is the same as what we'd written down in a much shorter manner here. And now what we're going to do is we're going to make use of the divergence theorem up here, because this is now in this form here. It's just that we've replaced our field with a specific electric field. And I can put a little s here to just show that that's a surface integral as well. And so now what I'm going to equate this to is that left-hand side of the divergence theorem. So that's equal to a volume integral times the divergence of our electric field, dV, in this case. And then we know from Gauss's law here that this must be equal to Q enclosed over epsilon naught. Okay, so now what we're going to do is we're going to have a little think about what Q enclosed actually means. So this is the total charge within a surface, and it's related to the charge density through the enclosed charge is equal to the volume integral of the charge density times dV. Now, just a note, I'm using dV here for the volume integral. Griffiths uses d tau. So d tau in Griffiths means the same thing as my dV here. I just find dV a bit easier because it's an increment of volume. So I just go with V. And this is rho here, which is the volume charge density. And so you know that if you need to get the total charge, you just integrate that charge density over the entire volume. So what we can do now is put this expression in for this up here. So we can now write, I'm going to take this bit here, down here, and I am going to write, we've got the volume integral of div of E dV is equal to Q enclosed, which is the volume integral of the charge density divided by epsilon naught. And because epsilon naught's a constant, I can put it inside that integral. So I can write this way. And so hopefully from that, you can see that because these are both volume integrals, this thing here must be the same as this thing here. So this means that I can write Gauss's law in vector notation as the divergence of the electric field is equal to the charge density divided by epsilon naught, which is the permittivity of free space. So this is the differential form of Gauss's law. Right, at this point, I think it's a good idea to see how we can use this to solve problems. So this is problem 2.9 from Griffiths, which tells us, suppose the electric field in some region is found to be E is equal to kr cubed times r hat in spherical coordinates. K is some constant. So this is a radial field, which increases as r cubed. And in part A, we're asked to find the charge density rho. And then in part B, find the total charge contained in a sphere of radius r centered on the origin in two different ways. Okay, so to start with for part A, we can make use of Gauss's law, which tells us that the divergence of E is equal to rho over epsilon naught. Now, a reminder, this question here is in spherical coordinates. And in spherical coordinates, we do have to transform our divergences. So just like we need to transform the thing inside the integral with the Jacobian, we need to do a similar thing for spherical coordinates when we're doing divs and curls. So Griffiths very usefully has all the spherical transformations summarized in a table at the very front of the book. But just a reminder for this one, we've got the divergence of some vector field V is in spherical coordinates. We can write this as 1 over r squared times the partial with respect to r. of r squared VR. So this is the r component of V, because this is a vector r theta phi, plus 1 over r sine theta times d theta times sine theta v theta, plus 1 over r sine theta d phi of v of phi. And in this case, our electric field only has the radial component, so the theta and the phi components are both 0. So this is the only part of this equation that we are going to have to use. Okay, so making use of this to solve this, we can write that charge density rho is equal to epsilon naught times the divergence of E. And then here we've got that VR in our case is equal to K r cubed. So we'll need to use this equation here. So this is epsilon naught times 1 over r squared times d dr of r squared times kr cubed. And so this is equal to epsilon naught on r squared times d dr of, this is kr to the 5. And so this is epsilon naught over r squared. The partial derivative of kr to the 5 with respect to r is 5kr to the 4. And then we've got this r squared on the bottom, so that'll cancel out with 2 of those. So this is equal to 5 epsilon naught kr squared. So part B asks us to find 2 ways to calculate the total charge contained inside the sphere. So I think the easiest way is just to go back to our integral form of Gauss's law, which tells us that E dot dA is equal to Q enclosed over epsilon naught. So we can just rearrange this and write, well, the enclosed charge is equal to epsilon naught times the surface integral of E dot dA. And this means the electric field over this surface. And we're considering a surface all at the same radius. And so our electric field here is constant over that surface. So when we're doing this integral, this electric field is constant, and the surface area, because we're just doing it over a sphere, is the area of a sphere. So this is equal to epsilon naught times the constant value that it has over that surface, which is kr cubed, because this is at radius capital R, so we're just substituting that into our electric field there, times the area of that surface, which is pi r squared. And we know that the electric field is radial, and our surface is also in the radial direction here. So this one gives us, this is equal to 4 pi epsilon naught kr to the 5. So that's done it a nice simple way, but now we probably better do it the full way as well. Okay, so like we said before, if we want to find the total charge within a volume, we can integrate the volume charge density over that volume. So if we want to do this properly in spherical coordinates, let's write this out. We've just worked out what rho was, the charge density in part A. So let's include that. That's 5 epsilon naught kr squared. And now we're doing a volume integral in spherical coordinates. So our Jacobian is r squared sine theta. And then we've got dr, d theta, d phi. And now we need to go through and put our limits on our integral. R is going from 0 up to radius r. Theta, that's the angle with the z-axis, so that's from 0 to pi. And phi, that goes all around the xy plane, so that's from 0 to 2 pi. And now we've got an integral that we can just step through and solve. So from 0 to 2 pi, 0 to pi, and we've got, let's just save writing this out in full again. You can see this is going to be 5 epsilon k r to the 4 sine theta. So when we integrate that with respect to dr, we're still going to have our 5 epsilon naught k, but then when we integrate r to the 4, we'll end up with r to the 5 on 5, and then we've got sine theta, and this is from 0 to r, and that's d theta d phi. And so let's pull our constants out the front, 5 epsilon naught k, and then from 0 to 2 pi, from 0 to pi, and evaluating this, the 0 one's just going to be 0, but this will be equal to r to the 5 on 5 times sine theta d phi. These 5s will cancel here, and so this will be equal to epsilon k integral from 0 to 2 pi. And now let's do the d theta integral. When we integrate sine theta, we get minus cos theta, and this is from 0 to pi, and this is d phi, and so this will be equal to epsilon naught k. And now when we put these in, we get minus 1, so that's plus 1, minus cos of 0, minus cos of 0, which is another plus 1 d phi, and so that's epsilon k is out the front, and then we're going from 0 to 2 pi, and we've got 2 d phi, and so this will be equal to epsilon naught k, and this will be 2 phi from 0 to 2 pi. And this, when we substitute in, we'll have epsilon naught k times 4 pi. And I've lost my r to the 5. Whoops, because I noticed that I had it up here. It's always a good idea to check. And you can see I had it on that line, but I forgot to bring it down to this line. So it should be there. It should be there. Should be there. And should be here. And should be here. Because we'd expect these two methods to give us the same answer if we didn't make a mistake. So we're now going to consider the curl of E for the electrostatic case. For the demonstration of this one, I'm going to diverge a little bit from Griffiths. I think probably the easiest way to see this relationship is actually to consider how we define the curl using spherical coordinates. So this equation is written in the front of the Griffiths textbook, and you will be provided with it if you needed it for an exam. To see where this comes from, there's a really excellent geometric proof of this in the book Fundamentals of Electromagnetics for Electrical and Computer Engineering by Rao, and that appears in Appendix B. So it's quite a long derivation, so we'll take it to be true. But if you're interested in seeing really clearly where that comes from, have a look at that proof. Okay, so we've got our equation here for the curl, and let's start by just considering a single charge Q. We know that for the electrostatic case, the electric field given by this charge can be written in this manner here, which we've been doing throughout this section. So this is a radial charge where all the field lines are radiating out from the particle. So from our intuitive understanding of curl, a curl is something that's going to make a particle start to swirl around, follow a kind of spiral path. And hopefully you can kind of intuitively see from this electric field is just not going to do that. If you put any charged particle anywhere here, it's just going to move away in a straight line. So intuitively, we can see that the curl of this electrostatic field should be 0. But let's just calculate it properly here. So we're going to be using this relationship above, and in this case our v vector is our e vector, and so that's equal to 1 over 4 pi epsilon naught q over r squared r. And so just breaking that into components, we've got VR is equal to 1 over 4 pi epsilon naught q on r squared. V theta is equal to 0 and V phi is equal to 0 because there is no component in the theta or the phi direction. So now what we can do is substitute these components up into our expression up here. And in that case, we've got del cross E is equal to 1 over r sine theta. We've got d theta, and this thing here is going to be 0, so that's of 0. So this thing here will be 0, and then we've got minus d phi of v theta, which is 0, and this is in the r direction, so this thing is also 0, so in the r direction it's 0. And then we've got plus 1 over r times 1 over sine theta dVr. Now that's not 0, d phi. Vr is not 0. This is equal to 1 over 4 pi epsilon naught q on r squared. But because this is totally independent of phi, when we take the derivative of this, the derivative is 0. So this thing here is also 0. And then we've got minus dr of r v phi, which is times 0, so that's 0. And that's in the theta direction, so this thing here is also 0, so we're still at 0. And then plus 1 over r times ddr, r v theta, which is r times 0. That thing there, also 0, minus d theta of VR, which is something, again, this thing here is 1 over 4 pi epsilon naught q on r squared. But again, this doesn't have any theta dependence. So when we take the derivative of this with respect to theta, the derivative is also 0. And this is in the phi direction. So in total, this is 0. So we can say that the curl of an electrostatic field is equal to 0, and we've shown that for 1 point particle, but this is true absolutely everywhere for that one particle. And because electric fields obey the law of superposition, it tells us that this is true no matter how many charges we have. So we'd still have del of E1 plus E2 plus E3 plus E4, etc. If we kept on adding those, it would still be 0. No matter how many times we add 0, it's still 0. So the curl for all electrostatic fields is equal to 0.